Welcome. We ended with kind of complicated looking figure. Not trying to overwhelm you, but there is some really interesting geometry to what's going on in these equilibrium regions near L1 and L2. And people have been trying different ways to view it. This was McGehee's approach. And the idea here was there is the Lyapunov orbit, right? We're looking at just one energy surface. For a given energy, there's going to be a Lyapunov orbit, and then the two sides in physical space, one side and the other around the Lagrange point, you could view those as being boundaries of the equilibrium region, and they both correspond to spheres. What we're viewing here on the right, the region between the two spheres is represented here, but don't think of it as one sphere is actually bigger than the other. This is just a geometric way of trying to illustrate it. So these minuses and pluses, this is all described in the book. Minus means things are going out of the sphere, like I'll draw here on the right, something that just kind of went out. And then if you were to backtrack where it came from this other sphere, which has a plus. Plus meaning it's entering, minus meaning it's exiting the equilibrium region. And that's all fine and good. Great, we can write the equations for it, but it doesn't really give us an idea of how these things look in the physical space. So that's what we want to talk about today. So I'm going to show a picture that I've shown a couple of times already, because this is sort of the regime that we're in, the energy regime. And we're going to look at what happens around each Lagrange point, and in particular in these things that we're calling the equilibrium regions, and we'll treat them the same. So we want to look at what's the appearance of the trajectories in the equilibrium regions around L1 or L2. And we could get that from the linearized analysis that we've already done. If you remember from last time, we said that once you translate the system so that the equilibrium point is your origin, then the linearized dynamics look like this linear time independent system. Y here is a matrix that actually represents X, Y, Vx, and Vy with respect to the equilibrium point, and just to generically refer to L1 and L2 as capital L. So this is all with respect to the equilibrium point, and we said that you can do a transformation to new variables via a matrix P. So either that, or you could write it this way, R equals P inverse Y. And what was P? P was a 4x4 matrix that was made up of columns that are eigenvectors corresponding to the different eigenvalues of the matrix A. So the unstable direction, or the thing that corresponded to both the coordinate C and the eigenvalue plus lambda, that was U1. The stable direction I called U sub 2, and that corresponded to a eigenbasis coordinate eta and the eigenvalue negative lambda. The first one is unstable, second one is stable. The next two are related to the oscillatory directions. So these are generalized eigenvectors that we were able to write analytically. So this first one we wrote, this was zeta 1, and this next one was zeta 2. And these both correspond to the plus or minus I nu, purely imaginary pair of eigenvalues of the matrix A. What is R? R is C, eta, zeta 1, zeta 2. And R dot was P inverse AP times R. For P inverse AP was a really nice looking matrix. And it made it so that all of these things were pretty easy to solve. So we had that C dot is lambda C. Eta dot is negative lambda eta. And then zeta 1 dot is nu zeta 2. Zeta 2 dot is negative nu zeta 1. And these equations are simple enough that we can analytically write the solutions. So if we were to solve, say, this first one, C as a function of time, it's going to be an initial condition, C naught e to the lambda t. So that's how the unstable, anything in the unstable direction is going to grow exponentially with this rate lambda. What about the stable direction? Well, very similar. Eta as a function of time is the initial condition e to the negative lambda t. These two are coupled, so the oscillatory solutions, if I write it this way, this is zeta 1 naught, so an initial condition, cosine nu t, plus the initial condition for zeta 2, sine nu t. That was zeta 1, zeta 2 is negative zeta 1 naught sine nu t plus zeta 2 naught cosine nu t. This is in the eigencoordinates. So we've got the solution to the eigencoordinates. In some sense, we've got the solution. We have the eigencoordinate solution. I'll call it R. Right? R is a function of time. We've got that. C is a function of time. Eta is a function of time. Zeta 1 is a function of time. Zeta 2. And that means we could also easily now get what it looks like in the original space. So I was using the vector y to represent the original space. So y as a function of time is using the coordinates. Here's xt, here's the scalar yt, vxt, vyt. And looking up here, right, what's the relationship between y and r? So the kind of original variables and the eigen variables, it's just this matrix P, R, which was what? U1, U2, U, and V. And let me emphasize, we've got R as a function of time here. P is constant. It doesn't change in time. So that's the P matrix. And then C as a function of time, eta as a function of time, zeta 1 as a function of time, zeta 2. And if you work out what this is, what do we get? Y as a function of time is, I'm going to write it this way. It's C naught e to the lambda t in the U1 direction, the U1 eigenvector, plus eta naught e to the negative lambda t, U2. Right, so these are just saying those are these unstable and the stable pieces. And then the other two we could write as zeta 1 as a function of time times the U eigenvector plus zeta 2 as a function of time times the V eigenvector, where the solutions for those based on initial conditions are given up here. I don't need to rewrite it. So that's instead of maybe writing it that way as y, let's emphasize this is giving the full 4 directions, x, y, vx, vy, with respect to the equilibrium point, right? Because this is a 4-dimensional vector. Each of these are 4-dimensional vectors. And in fact, the first entry of U1, U2, and U is just 1. That's from last time. And by first entry, I mean the x entry. So if we look at the x coordinate, And that's kind of what we care about the most. We can classify things based on what the behavior looks like in just the x direction. So let's just look at the x component. C naught e to the lambda t. That first entry is just 1 from the eigenvector. And then eta naught e to the negative lambda t. And then only u had something in the x direction. V had a 0 in the x direction. So we're left with just zeta 1 t. So that would be zeta 1 naught cosine nu t plus zeta 2 naught sine nu t. So this is the analytical solution of what happens to the x direction with respect to the equilibrium point. When we look at this, we can start categorizing things based on what happens as time goes to plus or minus infinity. So if you look at this, we go, okay, as if time goes to plus infinity, then x is going to be dominated by just this term, right? This thing will become 0, e to the negative infinity. It's going to become very small. These are just going to oscillate, but this one's going to grow. So we're going to be dominated by that term. I want to follow the way that the book writes things. And it says, instead of using C naught and eta naught, we introduce this, just a different notation. We call this alpha 1 and this alpha 2. And then alpha 1 and alpha 2, they're constants that come from initial conditions, but they end up being very consequential in terms of the behavior of trajectories. So as t goes to plus infinity, then x as a function of t is dominated by the alpha 1 term. In fact, you could start categorizing things. X tends to minus infinity if alpha 1 is less than 0. So x goes to minus infinity if alpha 1 is less than 0. It goes to plus infinity if alpha 1 is greater than 0. X doesn't go to either plus or minus infinity, meaning it stays bounded. I'll put that in the middle here. X of t stays bounded. Doesn't go to infinity if alpha 1 equals 0. And the same statement holds if we look at time going to negative infinity and replace alpha 1 with alpha 2. So we have a similar situation as t goes to negative infinity, but replace alpha 1 with alpha 2. So the signs of alpha 1 and alpha 2 give us categories of trajectories in this equilibrium region. So let me say that there's 4 categories of orbits. There's 4 categories of orbits based on the signs of alpha 1 and alpha 2. And it's probably best to just show a figure, and we'll sort of build up this figure and try to make that as big as we can. So this is the equilibrium region, and we're showing it sort of zoomed in. And now we're going to try to describe what's happening. So what is happening? Well, if alpha 1 and alpha 2 are both 0, let's look up here. If alpha 1 and alpha 2 are both 0, all we have is the oscillatory solution. Same thing with in the full 4 dimensions. So there's just oscillations. Now we're limiting ourselves to just one particular energy level. And so it's a little bit more complicated. And the results that I'm going to give here, this is actually based on a paper. Charles Conley had a paper in 1968. And I'll put that in the drive for you to look at. So I'm just going to summarize his results. For a given energy, so on the energy EL equals epsilon, we have 0 velocity curves. We know that separately, but we also have a single periodic orbit. And that single periodic orbit would be given by writing alpha 1 and alpha 2 equal to 0. So this periodic orbit is alpha 1 and alpha 2 equaling 0. You set those two equal to 0, you're just going to get something that's periodic. And it turns out it's going around the Lagrange point in a clockwise manner. Now things get more complicated for other combinations. Alpha 1 and alpha 2 equaling 0 means we're ignoring the exponentially growing and exponentially shrinking parts of things. We can include them, though. Let me say, before we get to that, we're showing an ellipse on the energy surface. So this is the 3D energy surface in the phase space. We've got a single periodic orbit, and it looks like an ellipse, a single periodic orbit. This is the thing that is called the Lyapunov orbit, which appears as an ellipse with a major axis along the y direction. It has a length of 2 times the magnitude of tau times square root of that energy, epsilon, divided by kappa. And I'll say what kappa is. And then the minor axis is the x direction with a length that's just 2 times square root epsilon over kappa. What's kappa? Kappa is negative a plus b tau squared plus nu squared plus nu squared tau squared. These nus and taus, a's and b's, were all part of how we formulated the linear system, and nu and tau are related to the eigenvector and eigenvalue. The main thing here is that you have an ellipse, and the ratio of the major to the minor axis is the magnitude of tau, because tau is negative. And it also scales with the square root of the energy. This is the energy above the equilibrium point. So that thing is going to be shrinking in proportion to square root of that energy. So that's the periodic orbit. The periodic orbit on each energy surface, there's just one periodic orbit. If you go to a higher energy surface, you'll have a larger periodic orbit, and so on. It just keeps on going. We're looking at sort of local neighborhood. That's where you can do the linear approximation, so infinitesimally small. But later we'll look at a numerical example in MATLAB, and it looks like this. You can actually get this in the full nonlinear equations of motion. All right, that's what we get for one category of orbit. And I'm using the term orbit loosely. Sometimes people think an orbit means something that has to close up. Mathematically, an orbit is it's the same thing as a trajectory, just in a system. Another synonym is integral curve. So don't think of an orbit as something that has to close up onto itself. All the solutions of an ODE are called orbits. So the next category of orbits are orbits that are asymptotic to this periodic orbit. So they wind onto it and they wind off of it. So those are the, like I said, asymptotic orbits. So here, let me give you an example of an asymptotic orbit. Something that comes over here and shows up, and maybe it's going around. Woo. And then it asymptotically goes onto this periodic orbit. You have that for alpha 1 times alpha 2 equals 0, but they don't both equal 0. In this case, this is an example where alpha 1 is 0 and alpha 2 is not 0. So this is an asymptotic orbit. So alpha 1, alpha 2 equals 0, asymptotic orbits. You could have things that are asymptotic onto the periodic orbit or also asymptotically going off the periodic orbit. When people were trying to describe the transfer onto the James Webb periodic orbit, they use terms like the transfer happens for free, because really you just get to an initial condition that's going to naturally want to wind onto a periodic orbit. This is very unlike what we're used to just looking at the two-body problem, but it happens here near these Lagrange points in the three-body problem. The asymptotic orbits are related to these strips that I've shown here. Conley labeled these. He was basically saying, look at the stable and unstable directions. So these are strips that are parallel to the stable and unstable directions. So alpha 1 equaling 0 maps to this strip that goes from the lower left to the upper right. And you could even write the equation for it. It looks like sigma x plus or minus 2, and then square root epsilon tau squared plus sigma squared over kappa, or it's the same kappa. That's giving these two bounding lines for this strip that we're calling S1, or that Conley called S1. Similarly, this other strip, we call that S2, and its bounding curves are very similar to this one. It's just that now there's a minus sign. It's y equals minus sigma x plus or minus 2, and then the same square root stuff we have below. That's what S2 is. This one is S1. These are the ones that have alpha 2 equaling 0, everything in there. And also notice that the width of these strips in which the asymptotic orbits live also goes to 0 with epsilon. So their width is proportional to square root of epsilon, meaning square root of the energy above the equilibrium point. Those are two categories so far, the periodic orbit and the asymptotic orbits. The other two types are called transit and non-transit. If we have alpha 1 times alpha 2 less than 0, that's a transit orbit. So let me give you an example of a transit orbit, something that does like this, maybe. Whoa. It might oscillate some, but it goes from one side to the other. So this is a transit orbit. They have alpha 1 times alpha 2 less than 0. And you've got things transiting from one side to the other. So it looks like they're sort of jumping from one strip to another strip. So that's one example of a transit orbit. You could also have things that going from, say, the right side to the left side. It's another transit orbit. Alpha 1, alpha 2, less than 0. The other category are non-transits. So you have non-transit orbits. They have alpha 1 times alpha 2 greater than 0. So for example, we could have something that, I'm kind of looking at that point right there, something that comes up here and then it just sort of leaves. And if you were to go backwards in time, this would be something that approached one side of this neck region and then left through the same side. Or you could just come through here and go back. You could have same thing on the other side, things that come in and then leave, or they come in and then they leave. So they don't transit from one side to the other. That's what we mean by transit. Basically, it means, does X change sign? Does X go from negative to positive or vice versa? In this case, no. Now, if you have a non-transit, X has the same sign the whole time. Conley had an interesting way to try to understand what these transit and non-transit orbits are like. And the situation is mostly complicated inside these strips. So he looked at what he called wedges of velocity. And he said, look at, say, this point in the lower left. There is a wedge of velocities, and I'll color that in purple. If you have a trajectory that passes through that point, everything in the purple wedge is going to be a transit orbit. Anything outside the purple wedge will be a non-transit orbit, and anything on the boundary of the wedge is an asymptotic orbit. We have alpha 1 greater than 0 in here, but everything along this dashed line is alpha 2 less than 0. And alpha 1 equals 0 along the edges of the wedge. And you can have a wedge of velocity everywhere. So here where this thing is exiting, this transit orbit here on the lower right is exiting, This would be the wedge of velocities. So we've got something that, because it did transit, it has to be inside that wedge. So the wedge is sort of an interesting visualization of what's going on. At each point in this domain, you could draw a wedge of velocities. So if a trajectory passes through that point and it's inside the wedge, it will transit from one side to the other. If it's outside the wedge, it'll non-transit. If it's on the boundary, you have an asymptotic orbit. So those are the four categories. What do we have again? We have a periodic orbit. We've got the asymptotic orbits. We've got the transit orbits and the non-transit orbits. And it's just related to the sign of alpha 1 and alpha 2, which come from initial conditions. You can design trajectories. You could pick initial conditions that do any of these behaviors near the equilibrium point. What do they do far away from the equilibrium point? Well, that's a separate question. This is sort of, we're looking here at what I would call the local dynamics. The question of what happens far away is more of a global dynamics question, meaning larger scale. In any case, whatever it is, it's really different than the two-body problem. I wanted to show, these are things that were computed in the full system. So you could see these things that we called strips. When you do the full numerics, they don't sort of maintain the same width. They do this weird shrinking, but kind of far away from the equilibrium point. If I were to just say, well, look at this part, it looks very much like what we expect from the linear picture. We have an ellipse. Well, it looks kind of like an ellipse. It looks like it's a slightly distorted ellipse. That's what you get when you get larger and larger energies, and you have to use different methods to find those. All the phenomena is there. So let's see. The next thing I was going to do is look at numerics. So I think we should try this numerically. We're going to look in MATLAB, do some MATLAB simulations of the full nonlinear ODEs, but guided by the knowledge that we've learned for the linear system. So I'm going to use a mu that's similar to the Earth-Moon system. So a mass ratio of the moon compared to this Earth plus moon is about 0.0121. And if we were to look at, say, L1, so here's the moon, here's the Earth, and we're looking in the, this is the X direction and the Y direction. It's centered at the center of mass of the system. I won't look at L2, I'll just look at L1. If I started with an initial condition that was slightly displaced from L1, starting at zero velocity, let's say I start right here. Do we have a guess of what would happen to that initial condition? So starting at zero velocity, what do you think this will do? Will it be in an orbit around the Earth, an orbit around the moon?
I would guess around L1.
Starting at zero speed? Because it's not at L1. We're going a little bit like to the left of L1. You still think it'll orbit L1?
I'm sticking to my guns.
Sticking to your guns. All right. I'm going to switch which screen we're looking at. I posted this interactive script thing, a live script. I just called it CR3BP Initial Exploration. And what I've got here is the mu value. First, I wanted to find where is L1. So if you remember, there was a fifth order polynomial, and this is how you solve a polynomial in MATLAB. You put the coefficients that would correspond to like the fifth order term, fourth, third, second order, first order, constant term. And then you can get the roots, and it'll give you the roots. All we care about is the one real root. So this shows us 5 roots, but 4 of them are complex, right? They have an imaginary component. There may be some quick way to get the real root. If there is, I don't know it. So I just sort of did this for loop where I look through all of these, and if they're real, then I say that's gamma. And so it gives me gamma. So gamma for this is 0.5107. Remember, that is the distance from the secondary, the mass M2, to L1. So if we want to say, well, where is L1? We put the location of the secondary, which is 1 minus mu, and then we subtract this. So the location of the Lagrange point is at about 0.8372. Okay. Everything else is 0, right? The Lagrange point is at 0.8372 in x, y equals 0, and then vx and vy also equal 0. Here's what I'm going to do. I'm defining the period of the primaries in non-dimensional units, which is just 2 times pi. And so I'll integrate for that amount of time. It's a nice time scale to look at. So I'm going to call that t final is 1 times t. I'm defining t span, which goes from 0, and then in increments of 1/1000th of t to t final. And I'm going to be starting with an initial x value. That's the location of L1 and just a little bit off. So 0.001 to the left. So that's my initial condition. If you haven't used MATLAB, this is what you would do to set an initial condition. So this is the x value, and then the other 3 are just 0. You can set things like tolerances. And I tend to like using ODE 7.8 rather than ODE 4.5. I just think it gives, it's just as fast and gives higher accuracy. And I've got a function I've written down below, which is the equations of motion for the CR3BP, planar restricted 3-body problem. And then you put in this, you can pass a variable. In this case, I'm passing mu, t-span, the initial condition, and then the ODE stuff. So this simulates that. And then I can get the x, y, vx, vy from this sort of vector of results. I've got a function that's in here that transforms from the rotating to the inertial frame, and I could pick which body I want as the center of that inertial frame. Let me just show the results. I started, that was my initial condition, the red circle, which was just a little bit to the left of L1, and it didn't orbit L1. It actually seems to be doing some weird thing going around the origin in the rotating frame. Now, in the inertial frame, you can get a better idea of what's happening. This looks like something that started out on a circular orbit, which is what staying at the Lagrange point would appear like, because we started out at 0 velocity with respect to the Lagrange point. But the natural dynamics wants to push us away in the unstable direction. So we get pushed away, and then we are on some kind of mostly two-body orbit around the Earth, which is M1 in this case. If for whatever reason we wanted to know, well, what does this look like in an inertial frame centered on M2? Well, it doesn't look like anything terribly useful because it's not an orbit around the moon. I've also plotted here the 3-body energy. So that's the thing that we've written. It's 1/2 the velocity squared in the rotating frame plus the effective potential. And you can see it doesn't vary much. You have these times where there's kind of big squiggles. One way to estimate the accuracy of your simulation is, well, how much does this change? So you could just calculate the standard deviation. Here I get a standard deviation of about 2 × 10⁻⁷, or something roughly on the order of the tolerances. So that's good. That gives me some trust. Now, in this case, I did the opposite, where I'm going to do an initial condition that's a little bit to the right of L1. Integrate for the same amount of time and all that. And maybe I'll ask again, what do you expect will happen now? For this one, where we were a little bit to the left, we got into an orbit around the Earth. What do you think will happen when we go a little bit to the right? Is it going to orbit the Lagrange point? It's going to orbit the moon. It's going to escape. See some chat. It'll enter an orbit around the moon. Hey, let's see. Let me go down here. I already ran this. And yeah, it does. So a little bit to the right of L1, and then we're on the other, right? There's the unstable manifold. There's 2 branches. There's 2 unstable directions. And this is what the other side does. Takes us to this, what looks like an oscillating orbit around the moon. The moon is here at 1 minus mu. So I didn't plot it in here, but it's roughly where my cursor is. Now, if we thought this was an Earth-centered orbit, this is what we would get, and it looks terrible. If we assumed it's a moon-centered orbit, it actually doesn't look much better. I guess these are kind of conic section orbits, but it's not clear. This is definitely in a three-body regime. And here's the three-body energy again, and you see maybe what looks like more wiggles. You get wiggles, I'm calling them wiggles. You get these oscillations in the energy when you get close to the central mass or at the furthest approach. So at perigune and apollune, that's what's happening here. But it doesn't change much. If I look at the standard deviation, it's still on the order of the tolerance. So that's good. Now, if I wanted to get into orbit around the Lagrange point, that doesn't just happen. They're very special initial conditions, but we actually know how to do that. If we basically set alpha1 and alpha2 equal to 0, then we can get it. So here I'm doing a calculation where I'm trying to get to the eigenbasis. So I calculate that mu bar thing. That was from the last lesson. And then A and then B. And this gives us both lambda and nu. So we analytically get the eigenvalues and then things related to the eigenvectors, which were sigma and tau. Remember, here's sigma, it's kind of small, 0.46. Tau, it's kind of large and negative 0.3, negative 3.5. And then we could define U1, U2, U, and V. So we're analytically giving the eigenvectors as columns. But all I want to do is I'm just going to start at the equilibrium point and then perturb in the direction of this U eigenvector. So this capital XL is just, this is the Lagrange point, but written as a four-dimensional vector. So it's at the location XL, and then everything else is 0. And then I'm doing a non-dimensional displacement of 10 to the negative 5. So my initial condition, XO, is XL plus this displacement times this vector U. So this initial condition should be only in the oscillatory part of the local phase space. And then I do all of the same stuff, integrate, plot, and what do we get? There it is. So you can kind of see the red circle is where we started. We displaced a little bit away from the Lagrange point, integrated for, oh, I didn't show what I integrated for. It was 2 pi over nu, which is in the linear system, that would be the period of one of these Lyapunov orbits. So I knew ahead of time not to choose too big of a displacement. I chose a small enough displacement that this worked. And it almost goes around and comes back onto itself. And it's in the rotating frame that you see, oh yeah, this is, a periodic orbit. And it looks like it roughly has the ratio I would expect. The major ellipse is, the size of the major ellipse to the minor ellipse is tau, and tau was around 3. That looks like something we have here. If we were to look at this in either an Earth or moon-centered inertial frame, it doesn't look like anything special. It just looks like roughly what the Lagrange point would look like. The Lagrange point moves in a non-Keplerian circular orbit around the Earth. And I don't know what it's doing around the moon. The energy here, because we don't have any close approaches, it's pretty rock solid. In fact, look, the standard deviation is basically machine precision. I could adjust this. That's the nice thing about these interactive things. I could play with it. If I tried, say, 10 to the negative 4, and then I'll run it. I think it's pretty quick. So for this large orbit, now you see, okay, it's deviating away, and this is just going for 2 pi over nu. If I did twice that, it's probably going to shoot off in the unstable direction going towards the Earth. That would be my guess. So if I say instead of 2 pi times mu, I do 4 pi times mu, and then run this. Right, it does automatic rescaling. So if I wanted to really see what's happening down there, I've got that tiny little periodic orbit. It's almost doing a periodic orbit, then it doesn't quite do it, and then it goes off in an unstable direction. And oh well. And now you can see what's happening in the inertial frame. It's sort of gotten away from the L1 point, and it looks like it's starting to be on an orbit around the Earth. If we viewed it as an orbit around the moon, doesn't really make much sense. And the energy behavior is still pretty good. If you want to see what these functions look like, this is the function that gets integrated. So this is standard for MATLAB. For you write things in first order form. This is the right hand side of the ODEs. I've got this energy thing. It just calculates that energy, 1/2 v squared plus u bar. And then to transform from rotating to inertial, there's also this other function. So I've put that in the Google Drive. You can play with it. You can kind of do whatever you want. I think that's it for today. That's all I had planned. Do you have any questions, or want me to try some initial condition? You do build up intuition by just playing with this thing and just trying stuff. Like I'm starting near L1, but there's really no reason I have to. I could do any kind of initial condition. Let's see. I'll pick something that's, say, close to the Earth. And then I'm not sure what to put for a velocity. I'll just put 1. And then if I do this and integrate, what will happen? I get this. It looks like a football or something. Yeah, I don't know about that. Maybe I'll stick with this other initial condition, but just follow it for a lot longer. Let's say 10 periods of the primaries. So remember, this was the one that it goes around the Earth, but now we see a lot more motion around the Earth and lots of close approaches to the Lagrange point. And every time it has a close approach, it's actually making what would be an orbit around the Earth. It's shifting it. So it's shifting its periapse. And so you get a bunch of kind of connected, weird orbits in the inertial frame. You could also see, it looks like the 3-body energy, at least overall, you've got these sort of spikes that probably have to do with close approaches to the Earth. And then overall, it's going down. So that might mean if this is going down too much, and I can't really tell you what too much is, but if it's going down too much, I probably have to increase the tolerance, but that increases the computational cost. So let me look at the standard deviation. It's actually not that bad. It's still 10 to the -7. I mean, if I did, instead of 10, if I did 100, I think this will just start looking like a big mess. Because we're in a chaotic regime. Sort of starting near the Lagrange points is the easiest way to get in a chaotic regime for the 3-body problem. And look, now we see the energy behavior. It's going down. This might be numerical dissipation, so maybe not so good. I would then want to boost this tolerance. Maybe I'll make this 10 to the -10, make this 10 to the -8, and then run. I think the appearance of the orbit won't really change much, but the energy, okay, the energy is now going up, but standard deviation is a lot less. So, yeah, you can see this is, it's looking like a big mess because it's chaotic. Yeah, I cleaned up some code I had written before. I think I even have it down here. It's kind of wild to think. I wrote this in 1997. So I guess it worked and I stayed with it. And this was written, again, 1997. So it's weird to look back at that library of things. But we could try a different mu. It's another cool thing to do. Instead of Earth, Moon, let me comment that out. Just say, well, what if I want something more like Jupiter, which is about 1/1000. And I think all the formulas will still work. So this is what things look like now with, it's not Earth and Moon anymore. It's more like Sun and Jupiter. You can see things, okay, things maybe changed a little bit. What about over here? Looks like it changed. What about the periodic orbit stuff? Yeah, I went too long down here. Let me change this to 2. And now you're seeing that this isn't quite coming back to itself. You could use a differential correction algorithm, a shooting algorithm. Basically, all you'd have to do is, in this case, you have to just change the y velocity. As you adjust the y velocity, you'll see this endpoint kind of drift around a little bit. I could even try that here. If I'll take, this is what I'll do, XO4, that's the y velocity, and I'll just increase it by 1%. So I multiply it. This is actually how I used to find things, and then I realized you could write algorithms and do like a Newton solver. Okay, so that didn't work. 1% was not good. Maybe I need to do 0.99 or something. That's 99%. So I'm subtracting 1%. Oh, okay. So it's somewhere in between those two. Maybe if I do 999. Okay, it's getting maybe better. 998. Also, what I have for the period might not be correct. This is just sort of a first guess. Yeah, we're getting better. It's getting better. If I do 9985. So this would be called shooting by hand or something. Oh, see, it's getting pretty darn good there. If I zoom in. Yeah, it's pretty good. So you can do some kind of optimization where you're trying to make this final point, the distance from the final point to the initial point, go to 0. And you could do that. That's what the algorithms that people use to create Lyapunov orbits are all based on that. Like, it's called differential correction. I think I'll be maybe talking about that sometime. But play around with that if you want. But I'm going to let you go.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series.